It's interesting to see the class kind of fill up in the morning. You would think that if the humans have to do it, then it would take about 5 minutes for everybody to check in. And if a computer had to do it, you would think it would take a fraction of a second. But it's somehow intermediate between those two, and I don't know why. Oops, let me get up the chat bar. All right, so how's everybody doing today? Do you have any questions for me about the material that we've been working on? All these the line integrals and surface integrals, especially the ones that involve vector fields. Any comments or questions that you need to bring forward? All right, well, my goal today, well, and we have just 4 days left, is to work through chapter 8, which is there's going to be a sequence of theorems that are actually very cool, very fun, but they're also very useful, both in the mathematical sense, but also in the applications to physics, well, physics and engineering, I guess, because a lot of these line integrals and surface integrals that we've been talking about, they have to do with physical phenomena, as we've already discussed, the work done and the flow of this, some kind of a flux past the surface. So it will be useful for us to be able to tie these various things in together. And that's what the theorems are all about. Now, just to put all this in context, let me tell you that at the end of the day, well, at the end of the century, as mathematicians had worked through all these separate theorems, they realized that actually they're all special cases of one theorem. If you just look at things in the right way, then all of the theorems we're going to see in chapter 8, you can sort of prove them all at once. And the most general form of this theorem is known as Stokes' theorem. And if we have time, by the end of next week, I'd like to show you guys something about how you put them all together and how you can come up with a common language that describes all of them. And that will subsume everything we're doing with the line integrals and the surface integrals. I will say that the formalism that puts them all together might seem a little foreign for the people who actually feel like they get it and what the line integrals and the surface integrals are showing them when I use the standard notation that we've been giving. But it is kind of nice. I'll try to hint over the next couple of days at how these different theorems tie together. So unless you have other questions about anything, I'm going to dive into that. We'll start chapter 8. All right, let's get this all lined up here. Okay, so chapter 8 is all about the theorems. And I'd like to remind you about one theorem in particular that you should already know, which is the fundamental theorem of calculus. So there's a few versions of the fundamental theorem of calculus that you know. One of them says that if you take any function and you integrate it from a fixed point in its domain up to a moving right-hand endpoint, then that becomes a function of t. This defines a function of t, if you like. For every t, you'll get a different number. Oops, sorry, for the dx. And well, once I have a function of t, then it makes sense to differentiate that and ask what you get. And as you guys may recall, when you antidifferentiate, well, when you integrate and then differentiate, it turns out you've come back to the original function. Of course, it's a function of t, not x, but this is one version of the fundamental theorem of calculus. The version that I would like to have you actually focus on today, though, is the one that says if you take any differentiable function, let's call it capital F, and, well, you differentiate it, now you have a new function of x, and if you integrate this function of x with respect to x, what you will get will be integrate this over a certain interval from a to b, what you will get will be exactly f of b minus f of a. So you guys are used to using this theorem. The way you've used it in this form is you say, oh, I have to integrate some function So I will try to figure out a function that this one is a derivative of. So in other words, I anti-differentiate to figure out the capital F, because once I've written that function as the derivative of something else, now I can compute that integral by simply evaluating capital F at 2 points. So now I'm going to do something a little different. I'm going to keep the same theorem, but change the notation a little bit, introduce what is going to feel like a funny notation. If you have a collection of points in the real number line, and you've assigned the numbers +1 or -1 to them, so you have a picture that just looks like, well, I don't know, you could have more than 2 points. But if I assign a +1 to some of them and a -1 to others, and let's call these points A, B, and C, then I would like to define the zero-dimensional integral of a function f. This would be a function of one variable now. But if I want to integrate this over the finite set that contains only the numbers A, B, and C, or however many points you've just indicated, I'd like to define this to be just the sum of the values of the function f at each one of these points. I'm not liking any of these markers today. The values of the function f at all of those points times the plus or minus sign that's been attached to them. So in particular, if you have an interval drawn and you make the decision to give the right-hand edge the +1 sign and the left-hand edge the -1 sign, then computing the zero-dimensional integral of this function over this set would now be exactly what you see on the right-hand side of the fundamental theorem of calculus. It's the plus or minus sign times each one of these things. Now, mind you, it's not quite the same as our other definitions of an integral, but in a sense it is. I mean, how do we ask you to evaluate any integral over any set? What I always tell you to do is to chop the set up into pieces, evaluate the function at each one of those pieces, and multiply it by whatever is the appropriate measure of a size for the pieces. So we've done that when the measure of size meant length, or when it meant area, or when it meant volume. But in this context, if I just interpret the size of a point, I mean, a point has got no real size, but if I just treat it as a +1 or a -1, so there's really essentially nothing to multiply by except to pick a sign for each one of those points, well, then the quantity that I've just written here or here, that just meets the definition of the integral that we've used in any other kind of a setting. And as a finite collection of points is what I have occasionally described this semester as being a zero-dimensional kind of object. We've talked about one-dimensional objects. Those are the curves. Two-dimensional objects were the surfaces. And three-dimensional objects would be the chunks of space. I don't know how to draw a chunk of space. There. That has a dimension of 3. And this concept of dimension made sense every time I encouraged you guys to do things like try to describe these sets with equations involving the coordinates. However many unknown coordinates there are of the points, you subtract the number of equations that you're writing down, and that tells you the dimension of the underlying set. Well, if you write down 2 equations and 2 unknowns, or 3 equations and 3 unknowns, you would be describing the intersection of 2 curves in the plane or 3 surfaces in space, and you know that in general that's just a finite number of points. And following the same rule of taking the number of coordinates minus the number of equations, this would be a zero-dimensional set. So exactly the kinds of things that I've been describing in these 2 examples, that would be a zero-dimensional set. I've put in this business of plus or minus signs, and we'll come to this, well, I guess I'll tell you, it plays the same role in the zero-dimensional sets as the 2 notions of orientation have been in our 1- and 2-dimensional sets. We've seen when you compute line integrals that you kind of need to know whether you're going this way on the curve or the other way. And computing the integrals in the one directions versus the other one, you'll just get the two of those integrals off by a minus sign. Well, that kind of made sense because of how we were interpreting those line integrals. It depended on whether or not a force was acting on us to make us go in this direction or in that direction. In the one case, you're doing a positive amount of work, and in the other case, a negative. In the same way on the surfaces, when we talked about surface integrals, we had to pick an orientation for this surface. We had to decide whether we were going to take our line integral with respect to the upward normal or the downward normal. And if you made the opposite choice, it would just change the sign of the integral. But you kind of had to have a pre-assigned notion of which way you were going to have the orientation for your surface. And by the way, if you had a one-dimensional set that was a union of a couple of different curves, you would have to pick an orientation on each one of those parts separately in order to apply your line integral calculation to whatever physical problem you had at hand. The same thing if you had a union of a couple of different surfaces, well, you'd have to pick out which is the normal that you think is relevant for you on each one of those separate surfaces. So what I was doing here when I was saying, you're just going to have to pick some of these points to have a +1 assigned and some of them to have a -1 assigned, you're just kind of going component by component and choosing one of the possible signs that you're going to put on your integral. So we had to actually work a lot to compute a surface integral. We had to work a little less hard to compute a one-dimensional integral, the line integrals. And for now, for a zero-dimensional integral simply means evaluating a function at a single point. So what I've tried to get you to see is that the kind of expression that you already saw on the right-hand side of the fundamental theorem of calculus can be actually thought of as a zero-dimensional integral of a function, of one variable. And then the way the fundamental theorem of calculus works is it says, if you want to compute a zero-dimensional integral of a function of one variable over the boundary of an interval, so again, I'll remind you that if the boundary, the edges of this interval would just be the 2 points. And so the zero-dimensional integral of this zero-dimensional set just means this difference of the two values of capital F. According to the fundamental theorem of calculus, this now says that you will get the same answer as if you had integrated over the entire interval from a to b. You integrate the derivative of that same function of x with respect to x. So here is a funny way of expressing the fundamental theorem of calculus. And I don't want to claim that it's more useful for you. It doesn't actually tell you anything different from what you've already seen. But I do want to stress the nature of this theorem because all of the other theorems in chapter 8 actually have the same flavor. What you're doing in this case is you're taking the integral of some kind of a function over the boundary of a set. And our theorems will all say that that kind of an integral can be rewritten as an integral of a different dimension. This is a zero-dimensional integral. This is a one-dimensional integral. This will say now that when you take if the boundary of S is one-dimensional, if that's a curve, and if it's the boundary of a set S, that S must now be a surface. Now we're talking 2 dimensions. So now I would be talking about a 2-dimensional integral over the interior of the set S. And what you would be integrating over is, in this case, going to be some kind of derivative of the function f. So 2 integrals will be equal. One of them is a lower dimensional integral and the other is a higher dimensional integral. One of them is over a chunk of space and the other one is over the boundary of that chunk of space. One of them talks about the one kind of a function f, and on the other side, you have some kind of derivative of that function f. So this will be all of the theorems that we have in chapter 8. They're all going to have that flavor. They're all going to tell us that two quantities are equal, and both of those quantities can be expressed as a kind of an integral. Exactly how you're going to use the theorem will depend on context. I mean, if you're just a mathematician, you say, I don't care how I'm going to use it, I just think it's cool. But for what you're going to be asked to do in the exercises and so on, you will typically be given one side or the other of this theorem, and then you will convert it to the other side and suddenly realize, oh, when I look at it on the other side, things are much easier. I mean, the boundary of a set is always much smaller than the original set, so that might make this side easier. On the other hand, when you take derivatives, they tend to look easier than the function you started with. So the applications will be up to us to figure out, but the theorems they'll all be of this flavor, and the fundamental theorem of calculus is actually the starting one. Okay, so that's a lot of yakety-yak, I know, but does anybody have any comments or questions on that much? All right, so after the fundamental theorem of calculus, which I called stage 1 of this set of theorems, the next one, the stage 2 in this collection of theorems, is going to be what's called Green's theorem. And it applies to, well, it's this kind of a situation here, but this is going to be done in the case where the set S is a bounded subset of the plane. Now, I don't know if you guys remember what it means for a set to be bounded. To be bounded means that you can enclose the whole thing in some giant disk. I don't want you to be taking S to be some sort of, I don't know, quadrant of the whole plane or anything. And then, what are we going to be integrating on this left-hand side? What I would ask you to integrate over, well, the boundary of S would be the thing that I'm going to call, the thing that I call little f up here is going to be one of these expressions, p of x and y, some function of x and y times dx, plus some other function of x and y times dy. So this is an expression that we have seen when I ask you to compute line integrals. You may recall that if I give you a vector field, capital F, that has two components, which I would call P and Q, then this is one of the notations that I wrote down for the line integral that asks you to compute the line integral of the vector field F dotted with this line element. Which was a vector. So you would write this in boldface in the book. That was one of the notations we used. Another one was we said, yeah, you're just evaluating this scalar valued function where you take the vector field F dotted with a unit tangent vector, and you integrate that with respect to length. And if you remember, that was a different notation that we had. And this third notation now is the one that I've just written. You write out the two components of the function vector field F. Those are the functions P and Q. And this is, you simply write the first function, you write the letters dx after it, and the second function with dy after it also. So this is where the capital P is related to, sorry, the P and Q are related to the vector field F by just being the components of that vector field. Some of you might like this notation better. You look at P times the unit vector I plus Q times the unit vector J. So those are the same vector. And if those are the component functions of the vector field, then you can write the same integral in all three of these ways. So we've used this notation before for line integrals, and that kind of line integral is what shows up in Green's theorem. If you have been asked to compute a line integral around the boundary of a bounded set in the plane, then Green asserts, Mr. Green, his first name was George, Mr. Green asserts that that integral can be written as an integral of some kind of a derivative of this vector field. And specifically, the way it works is, so here's Green's theorem. if S is indeed going to be a bounded subset of the plane, then when you integrate P dx plus Q dy over the boundary of S, you will get the same value as if you had computed an integral, it'll be a double integral now, over the interior of S itself. And what you're going to integrate will be, well, I said some kind of a derivative of this line integral thing, this vector field thing, and specifically it's this. You take the partial derivative of Q with respect to X and subtract the partial derivative of P with respect to Y. And that's your function that you integrate with respect to area over this set capital S. Now, I got one more little clarification to add to this, but let me first give you a picture so you have something to stare at. This would be the typical application, is that somebody picks out a bounded region inside the plane, so this is S, and then the boundary of S is the curve that wraps around the edge of this. So there are two different integrals to be computed here. If you've been given this vector field, maybe I should draw the collection of little arrows that goes everywhere. I'm used to this. So if this is the vector field capital F, you have to describe it with the two components, the P and Q. How far does the little arrow point east-west? How far does it point north-south? Given that vector field, you could compute the derivatives as shown here. Now this will be a function of two variables, and I want you to integrate that function of two variables over the set S. You could, for example, interpret that as being the volume of the region that lies underneath the graph of this function. Whatever. It's a number. On the other side, what you're computing is the line integral that says you walk around this curve, and at every point you know how we interpreted this before. You're taking the component of the vector field F that goes in the direction that you're walking. So once you have told me the value of the vector field right here, I would multiply that by the cosine of the angle theta that there is between the vector field F and the direction that I'm moving along the curve. Over around here, this seems to be pointing more or less this way. And if I'm walking this way on the curve, then I see a pretty big angle over there. That angle is more than 90 degrees, so the cosine of that would actually be negative. And so you'd be multiplying this, whatever the magnitude of your vector field is, by some negative number, close to -1 it looks like. And then you add up all those contributions as you walk along the curve. So again, it's an integral. We've been discussing line integrals. You kind of know what they mean, but I want to stress that that one is a one-dimensional integral. This is just a curve. To evaluate this integral, you would have to parameterize this with one parameter. You pick a t as your parameter for this curve, and then this line integral becomes an integral over a range of t's. So that's a one-dimensional integral, and this is a two-dimensional integral over the interior of this set S. Cool, huh? Or maybe just weird. Can I say it's weird? Now, one clarification I have to make clear to you guys. When we discussed integrals of functions of two variables over a chunk of the plane, we did all these calculations with Fubini and so on, and there was never any question of, like, which way, where's the unit normal? Well, that was not an issue. We had surface integrals later that kind of felt sort of like this, and that's when we had to have a unit normal vector, but not here. This is just, like I say, Fubini's theorem is probably how you would calculate this. On the other hand, I drew a vector field for you, and then I started to draw this curve, and I just instinctively put my little arrows going that way. But you know that when you compute a line integral, you have to decide which of the two directions on the curve is the one that actually applies to your physical situation. And I didn't give you guys a physical situation over here, so it's not clear which way you're supposed to parameterize this curve. So that actually is a part of the statement of this theorem. The boundary of S has to be oriented counterclockwise. And that I'll actually have to refine what that means in a minute, as you'll see. Okay? So there is a shorthand notation that says all of this stuff. When people have a physical set and they want to talk about the boundary of it, they just simply write the partial derivative symbol next to the set capital S. So that is a shorthand notation for the boundary of the set S, and it carries with it the understanding of how exactly you're supposed to orient your curve. In this case, it's a curve. And I'll be using this notation on the other theorems as well when we get down to the boundaries of stuff like a ball in three-dimensional space. Anyway, that's Green's theorem. It's actually not too hard to prove once you set it up in the right way, and I'll kind of indicate how it works by showing you an example. But yeah, I'm not going to require that you guys understand the workings of what makes the theorem be true. But let us, in fact, take an example. This will, I think, be an example that shows how the proof would work. So for my set S, what I want to take is a rectangle in the xy plane, because that'll make it easy to evaluate the integral on this side. So let's have a rectangle that's described with this kind of a notation that we've had before. It's called the Cartesian product of the two intervals. And that means that on the x-axis, you can have all the x coordinates that go from a number A to a number B. And on the y-axis, you let all the y coordinates simply vary independently from C to D. Doesn't matter what the x coordinates are. You have those y coordinates. So the Cartesian product, the set S, is now this rectangle. All right, do you want me to give you a specific, let's start with a specific vector field. So I want to write down some functions of x and y here. How about if I have just x squared y as the first component, and then on the second component, I'm going to put 3x plus 4y. All right, so Green's theorem will tell us that two integrals are equal. I don't, at this moment, know why I would care about either one of them, but let's just compute both sides and check that they really are equal. So on the right-hand side, you need to be able to calculate this thing that's going to serve as a kind of derivative of the vector field. I'll take the partial of q with respect to x minus the partial of p with respect to y. This is the p, this is the q. So the combination of partial derivatives would be just a 3 from the first term, and for the second one, I get x squared. So that's the function of two variables that I'm supposed to integrate over this rectangle, and that's easy enough to do. By Fubini's theorem, the right-hand side can be calculated as a double integral as x ranges from a to b, and y ranges from c to d of 3 minus x squared dy dx. The inner integral is actually easy to compute because I don't even have any references to y. As far as this inner integral goes, this is a constant, and so I'll just multiply that constant, pull the constant out, multiply that by the length of the interval of y's, which is d minus c. So there's your function of x that needs to be integrated. You now use the fundamental theorem of calculus. I told you there's a connection here between these theorems and the fundamental theorem. With the fundamental theorem of calculus, I now look for an antiderivative of this, and my antiderivative might be, let's see, what's a function of x whose derivative is 3? How about here? We have 3x. So somehow we're tying in with the original, with the original integrand. And likewise over here, I need a, oh, sorry, I shouldn't say likewise. And now to get an antiderivative for the x squared, I simply ask a Calc 1 student, get x cubed over 3, oops, sorry. And now I want to take the zero-dimensional integral of this function of one variable. That means I just plug in the two endpoints and subtract. And so you get whatever you get here. D minus c, you plug in both b and a for the x here, so you'll get 3 times b minus a. And for the other one, you'll have to plug in those two x's and cube them. So b cubed minus a cubed over 3. Yeah. So that's the thing that I call the right-hand side of Green's theorem. There's not a law that says which side is left and which side is right. But the other side of Green's theorem asks us to compute a line integral of pdx plus q dy. So that's, where did it go? That's x squared times dx plus 3x plus 4y dy. And that is to be integrated over the boundary of this rectangle. Well, the boundary of the rectangle is the union of those 4 line segments, but it has to be taken counterclockwise. So I'll actually take the sum of those 4 line integrals in the direction shown. I'll do them one at a time. So if I can call these curves C1, C2, C3, and C4, then this line integral will be the sum of 4 parts. It's, well, the integral over C1 of exactly this expression, plus the integral over C2, C3, and C4. Now, let me start to rewrite this into one of the other notations that we have for line integrals. Right now, it's using this notation. Let's reach for this one next. So I would write this as the vector field x squared y comma 3x plus 4y dotted with a unit vector that's, that points in the direction of motion along the curve. That's your scalar valued function that you're supposed to integrate with respect to length, with respect to arc length. And it would be the same exact expression in each of these 4 parts. All right, well, so how do you compute a line integral? The first step is to parameterize this curve. Now, each of these is a straight line segment, so it's actually very easy to parameterize it. If you start here at this point that's got an x-coordinate of A and the y-coordinate was a C, this other point over here has an x-coordinate of B and the same y-coordinate C. So a parameterization for this curve might be, you could take phi of t to just be t comma c, where you let the values of t range between A and B. That'll parameterize the curve for you. When you compute the first derivative of this, that is the vector 1 comma 0, and that is in fact the unit vector. It's a unit vector in this case, and it points in the direction that we're moving along the curve. So our method of computing the line integral says that this first one should now be the integral over this range of t's. Take your parameter and figure out what range you need for those. And what you're supposed to integrate with respect to t will be this dot product. You have to replace all the x's and y's by these functions of t. So I'll just get t squared times c as my first component, multiplied by the first component of u, plus, let's see, 3t plus 4c multiplied by the second component of my velocity vector, which is a 0 in this case. So, of course, all this drops out over here, and t squared times c is just t squared times c. And the integral of this thing now, I anti-differentiate with respect to t. I'll get t cubed over 3, stick in the 2 endpoints, and what you're going to have now will be c times b cubed minus a cubed over 3. And I went up because you got to remember that this was the sum of 4 separate line integrals, and I need to evaluate each one of them in the same way that I evaluated this one. I'm going to figure out a numerical value for the next, and the next, and the next. But in each one of those 4 cases, I want to do the same kind of work that I did here. I need to pick a parameterization for each of these 4 curves. And I can do something similar to what I did here, but there is a little catch that I want to make sure you guys remember to do. So here I would need to have a parameterization of this next line segment, the next curve. And all of these points have an x-coordinate of b, so the parameterization that I would use this time would just be b comma, well, t. And then in this case, I get all of this arc, well, it's a straight line segment, by taking the t's. The t's are the y-coordinates, and they vary from c to d. And you'll do something similar here, but be careful about it. All the points on this next path They all have a y-coordinate of d, so you would be tempted, I guess, to write phi of t equal to, well, t comma d feels right, and you know you need values of t that range between a and b, same as they were on the first curve. But unfortunately, this isn't giving me the right unit vector. You know, when you start with a path, a roadway, a line segment in this case, there are two ways to parameterize it, either left to right or right to left. And we're getting the wrong one out of this parameterization. This is giving us the unit vector that points east always. So this would not be a parameterization that I could use to capture the sense of computing this line integral. To compute this line integral, you need to parameterize this in such a way that your unit vector matches the direction of travel. So you have two options that I could propose for you. The easy way, I guess, is to say, oh, the parameterization that I just chose here takes the right curve, but it parameterizes it in the wrong direction. And, well, you're going to give exactly the negative of the line integral that you wanted to get. So you could use this parameterization, but just remember to change that to a minus sign at the end. I'm actually not
Dr. Risen?
Yes, please.
Could you like maybe turn off the light or something? Because like I think the glare on the paper is causing it. It's really hard to see right now.
I'm sorry, but actually the light is already off. I do see the problem. Maybe it's just the sunlight. I don't know where oh, is that where the light is coming from?
Would it be possible for you to scan these notes?
Maybe. I don't actually have a scanner. I mean, I have a printer scanner. It doesn't work very well. Yeah. I'm glad you asked me because that is important. Somebody asked me in my afternoon class too. I tried just about every marker now. It's not good. The problem is with all this zooming, I've dried out all my markers. Oh, maybe that's better for now. Yeah, Brianna, that's a good idea. I'm not sure. In fact, I'm going to be out of town this weekend, so if I do scan them, it won't be until a few days from now. But I'll see what I can do. And in the meantime, this marker, at least for a few minutes, it seems to be holding up. So let me just darken in some of the things that I was just describing. So this parameterization would get you to the right set of points, but unfortunately, it would parameterize the curve going from left to right as t varied first from A and then up to B. You would start here on the left and move towards the right, and that's not what you need. So you would need to put in a minus sign somewhere.
Could you just change the limits for the parameterization?
Well, yes, but that's because you guys are used to thinking about limits of integration as being just two numbers that you throw up there. I've been trying to get you guys to think about actual physical intervals that you integrate over. So I would like to say, well, you're integrating over the set of numbers from A to B. Yeah, you could say you integrate from B to A, but how do I write that as a parameterization? I mean, all of these little tricks, they're going to work. They'll give you the same answer, but I'm trying to get you guys used to one that I think is closest to the spirit of Green's theorem, and it's going to enable you to proceed on to other examples where it's not just rectangles. So, so let me propose this. What the kind of solution that I like best is to put in something where you actually literally give me instructions of where to be at time t that literally move me from right to left the way the picture originally showed. And so here's a couple of things that you might try. You might just say, well, you know, all the numbers kind of worked out all right, except I want to go from right to left. So you could put a minus sign right in there. And then you say that you need the values of t to range between minus b and minus a. And now the algebra, oops, sorry, minus a, I need to say it that way. And now the algebra works out the first value of, so negative b is a number that's smaller than negative a. If a is on the left and b is on the right on the real number line, then the negatives of those have negative b to the left of negative a. So in other words, you really are taking t's in an honest to God interval. Now that is trying the t's really are coming from an interval, but it's an interval that is lined up with the numbers that I just wrote there. That your interval is the numbers that go from minus b up to minus a. Another thing that you could try is to say stuff like this. You could say, well, you know what? I need to start at the point, my x-coordinate needs to start at a b, and then as time goes on, I progressively reduce that towards the number a. So you could use what we have often done for straight line parameterizations. If phi is supposed to parameterize a straight line from here to here, you could say I'm going to start at this point and then add in positive multiples, fractional multiples, of the vector that takes you from this point to that point. Now, these 2 points have the same y-coordinates, so the vector that goes from here to here would be just, what would it be? It would be a minus b. So you'd start at the point where you're supposed to begin, which is at the point b comma d, and then you add in multiples of the vector a minus b comma 0. I'm sorry, let's put that as a vector. So when t is equal to 0, at time 0, you are at the point b comma d, that's the upper right-hand corner. And as time increases towards time 1, by the time you get to time 1, you'll have a b plus an a minus b, which is the a that you needed in the first component, and nothing is changing in the second component. So this would be a parameterization that you could use. You could write out you sort of add the x and y components if you like. The x component is b plus t times a minus b, and then the y components, of course, are all going to stay constant at just a d. So as you move across the top edge of this rectangle, this would be a parameterization that you could use. Now this one has the feature that when you compute the first derivative, you won't get a unit vector this time. The first derivative would just be the vector a minus b comma 0. That's not a unit vector, but still we did learn when we discussed remember the magic that happens when you're computing a line integral. Turns out you didn't need a unit vector. You could just compute exactly the dot product that I showed over here. And then the length of this, the speed factor involved in your parameterization, that would cancel the fudge factor, the stretch factor that shows up in the computing of line integrals in general. So you don't have to worry about the fact that it's not a unit vector in this case. So here are a few ways that you can account for the fact that Green's theorem forces you to go from right to left. Somehow I want you to remember it, okay? So you can choose to put in the minus sign if you can keep your wits about you. You could try to choose a parameterization that forces you to move from right to left. In this particular example, you could actually see the unit tangent vector that you actually need as you move along curve C3. The unit tangent vector would be the vector -1 comma 0. That's the direction you want to move according to that little blue arrow. So any of those becomes an opportunity for you to compute this line integral the way Green's theorem says it needs to be computed. And you'll need to do the same thing on C4, because to parameterize the curve C4, you might be tempted to use the parameterization I used for C2, and it would get you to the right set of points. It just wouldn't take you there in the right order. So any of the tools that you guys have thought of or that I have given you here can be used to make sure that you get the right order, the right path, the right direction on that path and that path. Okay, if you get the wrong direction, the worst that'll happen is you'll be off by a minus sign. But of course, if you're changing the sign of just one of these four numbers that gets added together, well, then it's not clear exactly how to adjust your answer at the very end. So you got to do it segment by segment, if there are 4 segments on the boundary, and make sure that you get a parameterization that keeps the path going in the direction that's shown. Well, that's a lot of computation to do, but it will in fact give you the right answer. I've shown you what the integral becomes along the first edge of this. If you did exactly the same calculation on the third edge, the one that we just were worrying about, I might say that the integral over curve C3 with the proper orientation, you're supposed to take the vector field, the the P and the Q, and substitute in your values of X's and Y's. So the X's, if I used exactly the same parameterization that I felt was natural, like I did over here, then my X's would still be a T. My Y coordinates would now be, my Y coordinates would be D's instead of C's like they had before. So there's a factor of a D in there. And likewise, the second component would evaluate to 3 times T plus 4 times D. So that's the value of the vector field at each point that I'm traversing, but I'm supposed to take the dot product with the unit normal in the direction I'm headed, which in this case would be -1, 0. So those are the things that I need to add up. Sorry, I got carried away here. This integral over C3 turns out now to be this integral as t ranges from A to B. All right, so I can use the t's in the natural order if I remember to use the unit vector that points from right to left. And you integrate this with respect to t, and lo and behold, what you'll get will be something just like what I had here, with all the c's changed to a d. But since there's a minus sign here that wasn't there before, I'll get exactly the negative of d times the b cubed minus a cubed. So, of the 4 integrals that needed to be added together, when you add in just the integral over curve C1 and the integral over the curve C2, going right to left, what you will get will be this number that I had computed earlier minus this number that I just computed now, for a grand total of, it's exactly this. It's exactly going to be d minus c times the negative of b cubed minus a cubed over 3. So you're building things up properly. You've at least got half of the final answer showing up in the computation that you've done. And in case you're guessing ahead, you would be right. You'll get the rest of this by taking the integrals over C2 and C4. Each one of them would give you, each one of them would be 3 times d minus c multiplied by one of the 2 numbers, the a or the b, and one of them will bring in a minus sign because it's the curve along the edge of the rectangle is traversed in the opposite direction from the other one. So I'll let you finish the calculations there, but this is how you would end up computing the 4 separate line integrals, and you would get what turned out to be 4 components that add up to the same thing as we computed for the surface integral. So that's the illustration of Green's theorem. And I'm sorry that we have to worry about visibility on this. I don't know how to fix that right now. But in my remaining minute, let me just show you an application which is actually very useful. Suppose that I ask you to integrate the function minus 1/2 y dx plus 1/2 x dy. And I ask you to integrate that around the boundary of a subset of the plane, and I'll draw the arrow in the appropriate direction. So here's my curve. Any old curve, as long as it's a closed curve that comes back to where it starts and is going counterclockwise around the region that it has just enclosed. Well, it's a line integral, and I would let you calculate it. Of course, you'd have to parameterize the curve and so on and so forth. But by Green's theorem, what you're going to get will be the integral over the interior of that curve. of what? You're supposed to take the partial derivative of this one with respect to x minus the partial of this one with respect to y. And that you do that surface area integral. Of course, that's just a 1. And when you integrate 1 with respect to area over a set S, you know that what you get is the area of the set S. Maybe you're not impressed, but let me show you what that tells you. This tells you that it is possible to calculate the area of a two-dimensional region by simply walking around the edge of it and measuring things as you go. I'm not computing the perimeter of the region. I'm actually computing the area of the region that's on the inside, and I never actually have to walk in there. This is actually a kind of a cool thing. I mean, if you are a surveyor and you need to figure out how many square miles there are of a region or square feet or whatever, you could do that by simply walking around the edge of your region with a tool. It has to be a tool that can compute line integrals as you go, but it's actually possible to manufacture that kind of a thing. In fact, you could make a handheld device that does the same thing, and then you could trace along the boundary of, let's say, Texas on a map, and then look at your little handheld device, and somewhere on the display it would say the number of square miles that Texas consists of. So this is a very cool thing. It's the device that makes this work is called a planimeter, and well, apparently you can buy them for about $100 or less, and it will actually compute the area of a region for you on a map by simply tracing out around the boundary of it. And the reason that it works is because of Green's theorem. All right, I ran over. I do apologize. I'll see what I can do by Monday to get the better visibility. In the meantime, have a look at, it's the first section or two of chapter 8. That's where Green's theorem is discussed. And there's even a proof in there for you if you're interested in that. All right. Any other comments or questions?
Dr. Rustin?
Yes, go ahead.
Well, here you only got it to work because you set up your function in a way so that when you take the partial derivatives, it just ends up being a constant, right?
Yes. But see, this is the thing. Green's theorem is a double-edged sword. There are times when the thing you know you want to compute is easily expressed as a two-dimensional integral. Fine. In that case, see if you can figure out a function of x and y for which this q dx minus dp dy turns out to be the thing that you had to integrate. So you have to sort of anti-differentiate the function of two variables that you wish to integrate over this two-dimensional set. And by doing that, if you can anti-differentiate it, you will have a line integral to compute. And maybe that would be easier for whatever reason. Or sometimes you're just given the p and the q and the curve that you're supposed to integrate over. Somebody wants you to compute a line integral, and a lot of you guys hate line integrals because you don't like to parameterize the curve or whatever. Whatever your rationale is, if you don't want to do a line integral now, you don't have to do it. Of course, what you're going to have to do instead is you'll have to integrate and do a two-dimensional integral over some chunk of the plane. But, you know, that's Fubini's theorem, so maybe that's easier for you. So Green's theorem lets you go either way. There's some things that you do have to worry about. I mean, you have to ask yourself, is the function that I have been given on this side, can I write it as a dq dx minus dp dy? Then, and that's maybe hard to go in that direction. And likewise, to go in this direction, you're not going to get away from computing all line integrals this way, because this will only handle the case where your curve is a closed curve. But even in with those constraints in mind, there are ways to kind of push ahead a little bit and use Green's theorem to simplify things for you a little bit. So I'm not claiming that we've reached the end of what there is to say about Green's theorem, but we have reached the end of what the clock allows us to do. So I don't know what to say right at this minute. Any other last short questions? All right, stay tuned then. On Monday, we'll do more examples of Green's theorem so that you can see some of the ways to use it for things like curves that are not closed and so on. All right, have a good weekend, guys. Stay healthy, and I'll see you on Monday.